Okay, now we want to see in the next part of the video, we're going to talk about how can we determine the reduction potential of any half cell. Well, we have to connect it up to a hydrogen electrode. So there we go. We have a voltaic cell. We're running zinc and probably zinc sulfate, and we have the hydrogen electrode, the standard hydrogen electrode, with acid. We have our salt bridge, and we have a voltmeter. Okay, so first thing we have to do is determine what's going on. Okay, we know a couple things from the previous section. We know that reduction takes place at the cathode. Okay, so cathode is where reduction takes place, and oxidation takes place at the anode. So they have them labeled for us. So reduction must be occurring here, and oxidation oxidation occurs here at the anode, and reduction takes place at the cathode. So what's happening is we're producing more and more hydrogen over here, and the zinc is wearing away. Okay, and of course we have migration of ions across to keep the solutions neutral. All right, so what do we know right now? We know that the cell potential, we've measured it as plus 0.76. All right, so we know that this is 0, dE of the hydrogen. We know is 0 volts because that's given. So now we're going to figure out what the zinc half cell's value is. Okay, so the voltmeter we see gives us the value of 0.76, as I mentioned. It's positive 0.76. And since the zinc is at the anode, electrons are flowing from the anode to the cathode, the zinc is oxidized and the hydrogen is reduced. Okay, so that gets us ready to figure out what our cell reactions are. And here we see the two half equations and the cell reaction equation. We've done a lot of these already. Now we're ready to determine the standard reduction potential by using our equation. So the equation we're going to use is right here. The cell, that's going to be from the voltmeter. We said that the zinc was being oxidized and the hydrogen was being reduced. So now we're ready. We know this because we said this was plus 0.76 volts. We know this because we said its value is 0 volts, and we can basically solve for this by basically subtracting 0 volts from both sides. So the zeros from both sides, so the 0.76 equals minus E, so this is going to be E 0 zinc is going to equal minus 0.76 volts. Okay? And there we go. So the hydrogen electrode is very important because we can find it 0. Experimentally, we can find E cell, and then we can determine what the E of the voltage of the one we're looking for is, the half cell we're looking for. And we just use that equation to calculate it each time. Now, fortunately, you usually do not have to do this experiment. Someone's already done this for you and has created tables with this information in it. So to summarize, the reason we have a negative number, it shows us the tendency of the zinc ions to be reduced to zinc metal in this cell is less than the tendency of hydrogen ions to be reduced to hydrogen gas. So if it's negative, if the standard reduction potential is negative, it means that the one that's more positive is going to be reduced. Okay, so it's a little bit different than the activity series. So here we are. These are half cell potentials. So if we look at this chart, and I would stop the tape and take a screenshot. So stop the tape right now. Take a screenshot. You might want to print this out so you have it, okay? Because I'm going to start marking it up a little bit. All right, so if we look up here, these tend to be, as we go, continues on from here to here. You'll notice minus 3.05 and plus 2.87. So it's a continuous chart, first column, second column. So the things up here will tend to be oxidized, most likely, okay? And if something's below it, that's going to be reduced. So something like fluorine wants to be reduced. So if you had lithium in one cell and fluorine in the other cell, you're going to have this reduction going on. And the lithium is going to be oxidized. Okay? All right. So now, since we have this chart, notice 25 degrees, 1 molar. We can assume 1 atmosphere if it's a gas. These can help us calculate what the voltage of the complete electrochemical cell is, because now we have the half reactions voltage. And we just used the equation we had before. And so there you go. All right, let's do this in Educanon. We just did the last question in Educanon. Let's do this one in Educanon. You're going to need to use the chart that I had just showed you. And we have to decide which of these two things will occur as an oxidation. So iron turning into iron will be accompanied by which of the following? So we have to look at the activity series. All right, look at the activity series and answer this question on Educanon. That's right, it's aluminum, okay? Aluminum will be oxidized, so aluminum must be higher than iron. Let's go back and make sure that's true. So here's our chart. So let's find aluminum. Here's aluminum. Here's iron 2, but I think we had iron 3, which is way over here. So things that will be reduced, this is going this way, okay? That's more likely. And if we had iron 2, we would still get a correct answer because it's going that way. Aluminum is going to be oxidized because it's higher up on the chart. Okay? All right, what makes it spontaneous? Okay, this is a definition. Okay, the E0, oops, sorry. The E0 value of the whole cell, okay, has to be positive for it to be spontaneous. And we can predict that without actually putting a cell together by using the table on reduction potentials. Okay, so that's the first thing we have to do. We have to basically decide what we have and then decide if it will be spontaneous. Okay, so if the E0 here so if the E0 here, that's the cell potential, of the cell is positive, okay, then it's spontaneous. Otherwise, it's non-spontaneous. So if it's negative, it's non-spontaneous. All right, so let's look at this reaction. Okay, zinc here is being oxidized, and silver is being reduced. Okay, so that means that this should be the zinc reaction should be higher on the table. Okay, and this should be lower. Okay, so let's see. So we know that E cell, okay, we want to identify everything. We know that it's spontaneous if E cell is positive, the reaction is spontaneous. Okay, these are the cell reactions we're looking for. We notice that that was oxidation and that was reduction. Okay, then we look up at the table. Okay, so everything on this slide is what I've just shown you before, except for this part. So the standard reduction potential for that is minus 7.6, and this is plus 8.0. Now this one here and this one are the same. So they're our reduction, and we said this is our oxidation. The actual equation of this is reversed, but we don't have to worry about that. But this tells us here that we know that this is going to be based on our equation. We know this is an oxidation. We just look at the reduction potentials because our formula will take care of changing the signs for us. All right, so if we look at this table now, we see our E cell reaction. So we have E cell. What is reduced? That was the silver. So we put that in like that. Then we have a minus sign, but we see the minus sign tells us that this likes to be oxidized also. Okay, when we add that together, the two minus signs cancel out, so we get a value of 1.56. This is greater than 0. It's spontaneous. So as long as the E cell is positive, it's spontaneous. That's all you have to remember. E0 is positive of the cell, the complete cell, not the half cells. Okay? Remember that these two things are the half cells. One part is the reduction, one part is the oxidation. So in this case, silver and zinc. We just look those up on the table, and then we tell if something's spontaneous or not. Okay, as I said, zinc is above silver. It takes, on the activity series also, it means that zinc likes to be oxidized. So the two tables kind of agree with each other, even though they're written in a different way. Okay, let's determine the cell reaction for a voltaic cell composed of the following half cells. Okay, so we have Fe3, okay, going from that, you add an electron, you get 2 plus. Now, the more positive one will be the one that's going to be reduced. So this is going to be our reduction reaction, and this should be our oxidation reaction. All right, I can write the two equations, but basically, if we know that, I can say E cell equals E0 Fe 3 plus minus E0 nickel 2 plus. Substituting in, we get plus 0.77 minus a minus 0.25, and that's going to be equal to 1 plus 1.02. Okay, volts. Let's see if we did it right. Okay, so as I said, the half cell with a more positive reduction potential is going to be where reduction occurs. That's going to be the cathode. Oxidation is going to be the other reactions. We can add the two reactions together so that we can see what it looks like. We can identify the cathode. Okay, we did that. All right, so here's our two half equations. The nickel, as I showed you, going to being oxidized, and the iron being reduced. In this case, we're only going to reduce it by 1. So let's go back and just look at that. See, that only went up by 1. All right, then we have to say our electrons have to be the same to cancel out before we finish up. So in this regard, when we're doing our balancing the equation, we have a special case here because the iron only needed 1 electron. Okay, so the iron only needs 1 electron, but to make this work, we have to have 2, so we multiply everything by 2. So we'd have 2 Fe3 pluses, and we'd have 2 of these, and the electrons would cancel out. Okay, so then our electron equation is nickel metal plus iron 3 plus will give us nickel 2 plus and 2 iron 2 plus. So it doesn't form iron itself, it only gains 1 electron. So it goes from Fe3 to Fe2. And notice the coefficients. This is another way to balance the equation. Okay, notice the coefficients here and here. That's because of these when we multiply through to get the 2 electrons to cancel out. All right? All right, and then I said let's look at the cell potentials, which I showed you before. That's our 2 values. We put in the formula, and we get plus 1.02 volts. Okay? And it's positive, so if it's E0 is positive, it's spontaneous. So we can say that this reaction is spontaneous. Okay, so here's a question for you. I'd like you to answer this on EdgeCanon. I've given you the values of each of the half cells. Okay, this is a little tricky because they're both negative, but remember what we said before, and go answer it on EdgeCanon, and then come back and we'll talk about it a little bit more. All right, so if we wrote everything there, we can see that the one that's more positive is going to be what? The one that's more positive is going to be reduced. Okay, so in this case, this is closer to 0, so it's more positive, so the iron is reduced and the aluminum is oxidized. Okay, so aluminum will produce 3 electrons and iron will want 3 electrons, so we don't have to multiply anything. So here's our equation. Aluminum is being oxidized, iron is being reduced. Okay, so then what we need to do is look at our values. Okay, so we are going to basically then calculate we're going to calculate E0 cell equals E reduction minus E oxidation, okay, of the oxidized side. So all we do is we said that ERED is minus 1.66 minus a minus 0.036, well, that's going to be a problem then, because that's still going to be minus, okay? So you're going to get a negative value. It's not spontaneous. Okay? So it's 1.66 minus minus 0.036. So if we do that, we would get over here 1.66 36, or yeah, 0.36 0.36. So we could simply do it this way. So we're going to get a minus 1. Well, let's just round it, 1.62. So that's your answer for sig figs.